Okay, guys, today I want to go over the next part of 7-1, 7-2, which is talking about reaction mechanisms. So I want to discuss what a reaction mechanism is, the information we can get from reaction mechanisms, and later I'll do another video lesson kind of going through some different practice problems with the stuff we've covered so far in Unit 7. But let's just get into it. So remember, last time we talked about coming up with the rate law for a reaction. And so we say rate equals K times, the concentration of one of the reactants raised to whatever order it is, right? It can be either 0, 1, or 2. And then we have all the reactants in the equation. And one way to determine the reactant orders is through different trials where you varying the concentrations of the reactants and you see how the rate is affected. So if you double the concentration of this reactant and the rate doubled, then you know that reactant A is second order, or sorry, first order. But if you double the concentration of A and the rate quadrupled, then you know that A is second order. Okay, so one way, if you're given that kind of experimental data, you could figure out the reactant orders by seeing how changing the concentration of each reactant changes the rate. But remember, the other thing I said was another way to figure out the reactant orders is if you know the reaction mechanism. Okay, so if you're given a complete reaction mechanism, you can also, from the mechanism, figure out the orders and therefore figure out the rate equation for the reaction. So that's what I want to get into today. So what is a reaction mechanism? What are the different components of a reaction mechanism? And how, if I was given a reaction mechanism, how can I find the rate law, the rate equation for the reaction? But also, if I'm given a partial mechanism, meaning not all the information in a reaction mechanism, but I know the rate equation, then I can figure out the rest of the information that's missing from the reaction mechanism. So, basically kind of knowing the rate equation can give you information about the mechanism, or knowing the mechanism can give you information about the rate equation. Okay, that's what we want to get to today. All right, so let's jump into it. All right, so whoops, let me get that off the screen, maybe. Okay. So first we want to understand what a reaction mechanism is. So let's look at this reaction. Okay, so it says 2A's plus 3B's and a C yield D plus E. So this is some chemical equation. Okay. So the first question is, do we think that this reaction might happen in one step? And your answer should probably be no. We wouldn't expect this reaction to happen in one step, meaning that these are the collisions that occur to form D and E. And the reason that is because we have 6 total particles. So this equation is telling us that if it happens in one step, it's saying that 6 particles all have to collide at the same time with the right orientation, with the right energy, and if that happens, the reaction can occur. And the odds that 6 particles would end up colliding at the same time, at the right same, or if the exact correct orientation with the right amount of energy is very, very, very low. So if this reaction were to occur in one step, it would be incredibly slow because, you wouldn't get many of those collisions that result in a reaction. Okay, so reactions tend to happen in multiple steps, and the outline of each step is what a reaction mechanism is. So really a balanced chemical equation tells us is the stoichiometric ratios between everything, right? So I can look at this, if this is the reaction that's occurring, I can say, okay, for every 1D gained, I lose 2A's, or I lose 3B's, or I lose 1C. So I'm losing B 3 times as fast as I lose C. I'm gaining E 1/2 the speed that I'm losing A, right? That's what those coefficients tell us. And they tell us the overall reaction, but that a chemical equation doesn't necessarily show each collision that has to occur for the overall process to happen. And that's what a reaction mechanism is, all right? So let's say this is our reaction mechanism. So a reaction mechanism shows the different steps that lead up to the overall reaction. So what this is saying is, okay, let's go back. This is the reaction that's occurring, but the mechanism tells us how it occurs. So the mechanism is telling us that A plus B, A collides with B and forms D and W. And then W, B, and C all collide together to form a Z. Z collides with another A to form a Y. And then Y collides with a B to form an E. And what we would do is if we add these steps up, we would notice that W cancels out, right? We would notice that Z cancels out. We would notice that Y cancels out. And what we're left with is 1, 2, 2 A's plus 1, 2, 3, 3 B's plus 1 C yields a D plus an E. And that is the overall reaction that we described above here. So the steps of the mechanism have to add up to the overall reaction. All right, so if we add these elementary steps up, and that's what a single step of a reaction mechanism is called an elementary step. What an elementary step is a collision that actually occurs. So an elementary step shows the collision that needs to occur. It doesn't show you the right orientation, but this is telling me that A has to collide with B. And if that happens, then we can get a D and a W. And then these three particles all have to collide to form a Z. And then a Z is now, once Z is created, Z can collide with another A particle to form a Y, and so on. So this is showing the collisions, right? So this is an elementary step, that's an elementary step, that's an elementary step, that's an elementary step. And if you add them all up, you get the overall reaction, okay? So that's our reaction mechanism. It's showing the collisions that have to occur for the overall reaction to take place. And what we want to show now is just a definition of something. W, Z, and Y, they're in our reaction mechanism. And, just given the overall reaction, it says nothing about W, Z, and Y. Okay? So just looking at the overall reaction, we didn't know they existed, right? We didn't know that W and Z and Y were a part of this reaction process. It's only through the mechanism that we kind of get deeper into the reaction that's taking place, and we see these things that are formed. And these things that are formed within the reaction mechanism are called intermediates. Okay? So we'll talk about an intermediate here in a second. But all right, so the elementary steps show the actual collisions that must occur for the reaction to take place. So this is a reaction mechanism. All right, so here's my overall reaction, but this is how the reaction happens. All right, that's what a reaction mechanism shows us. All right, so a multi-step mechanism will have what we call intermediates. So we just kind of introduced what those intermediates are. So if this is my reaction mechanism, if these are the steps that have to occur, notice that they add up to the overall reaction that we were highlighting at the beginning. And we have these new things showing up, W, Z, Y. Those are called intermediates. So this reaction mechanism has 3 intermediates, okay? And the way to know you have an intermediate is number 1, notice the intermediates are not included in the overall reaction, so they cancel out. But this is how they cancel out in the reaction mechanism, and this will be important later when we get to something called a catalyst, all right? They cancel out this way, on this diagonal, okay? And what we mean by that is they get produced and then they get consumed. So in a previous step of the mechanism, they get produced, but then in a subsequent step, they end up being consumed. So overall, they don't show up in the overall process, but they get produced and then consumed. A catalyst is the opposite, but not every reaction mechanism will have a catalyst. And we'll get to that in a second. All right, but how do we know what intermediates are in a mechanism? They are produced and then consumed. Okay. So what I just showed you was not a complete mechanism. For a complete mechanism, I have to be given more information, and you'll be given information like this. They're telling you that this first step happens fast, and the second step is slow, and then this step is really fast, and then that step is fast. So what they also, a mechanism, if you have a complete mechanism, or you want to show a complete mechanism, what you have to show is the rate determining step. You have to know which step in the mechanism is the rate determining step. And so let's think about it. How fast can you go? You can only go as fast as the slowest person, right? So if we took our entire class and we went outside and we ran a lap, and the time stopped when the last person crossed the finish line, we're only as fast as their slowest person, right? So a reaction is only as fast as its slowest step. So the slow step is the rate determining step, the RDS. So before, if this was all I was given, the different steps, well, I don't know which one is the slowest step. I might be able to predict that maybe this would be the slowest step because it has 3 particles that have to collide versus 2. And so this might happen slower. And that would be a good guess. But you don't know. You don't know which step is the slowest step. Maybe this step has a very high activation energy, so it's slower than that step. Who knows? All right. So in order to have a complete reaction mechanism, this works because it gives me my entire, it adds up to my overall reaction, but it doesn't tell me the rate determining step. So this is incomplete. So a complete mechanism would look something like this. Okay. So I was given, and you know, sometimes they say very fast, very slow. So if you had slow versus very slow, the very slow one is the rate determining step. Okay. So that's telling us that the second step of this mechanism is the rate determining step. All right. Okay. So 2 things must be true about a reaction mechanism. The steps have to add up to the overall reaction, right? So, you know, if you have some intermediates, they have to completely cancel out, right? When you add them up, kind of like you're doing a Hess's law problem, when you're adding up the equations, they have to add up to the overall reaction. And then they also have to agree with the rate law for the reaction. Okay. All right. So that means if they have to agree with the rate equation, that means if you know what the rate equation is, then you should be able to figure out the rate determining step of the mechanism. Or if you know the rate determining step of the mechanism, you should be able to figure out the rate law, the rate equation. All right. So that's what I want to do here. All right. So this is the reaction. And based on this mechanism, all right, this one where the second step is the slowest step, okay, the rate determining step, then this right here would have to be my rate equation, okay? So what that mechanism is showing is A and C are both first order reactants, but B is second order, all right? And if we wanted to find the units of K, the rate law constant, it would be 1 over molarity cubed because the reaction order would be 4, 1 plus 2 plus 1, and then whatever our unit of time is. But that's just kind of review from the previous lesson. So let's go back. Let's see how that reaction mechanism gives us these reactant orders. All right. So again, it's important to know the rate determining step because when figuring out the orders of reactants, you use the rate determining step and any previous steps to figure out the reactant orders. You do not use any steps that follow or subsequent of the rate determining step. So if this is my rate determining step, I'm going to look at just this part of the mechanism to figure out my reactant orders, and I'm going to ignore these steps. So what I do is I just go to the rate determining step and I look at just the reactants only. You don't include intermediates. And you look at the reactants only, not any of the products, the reactants only, and you count how many times a reactant particle is in a collision. So in the rate determining step, and then any steps before the rate determining step. And the number of times it's involved in a collision is its order. So if we look at the slow step and every step above, there's one C particle and there's one A particle. So that's why A is first order and C is first order. They're only involved in one collision. Or only one of the particles is involved in a collision before the rate determining step. But notice B shows up twice, so B is second order. Okay, so because this was the slow step, C and A are first order because they are only involved in one particle of each is involved in a collision, but two particles of B are involved in a collision, so B is second order. Okay, so based on this reaction mechanism and this being the rate determining step, I know that that's my rate equation for this reaction. I know the rate equation would be rate equals K times the concentration of A times the concentration of B times the concentration of C, and I'd have to figure out what those exponents are. And remember, they're not 2 and they're not 3 and they're not 1 unless this was an elementary step. Okay, you have to figure out the reactant orders based on data or a mechanism. So if I was given this reaction and asked to find the rate law, and then I was given this reaction mechanism, I can look at the rate determining step. I count C one time, I count A one time, so I know they're both first order, and I can count B twice, so I know it's second order. Okay? All right. So that mechanism that we had just gone through, it showed A and C as first order, and it shows B as second order. Okay, and so that would be my rate law, my rate equation for the reaction. Okay. All right. What if we were told the mechanism and we were given the rate equation? Okay. So what if this was my reaction and they said, hey, here it's the same reaction we've been looking at. This is the reaction, but this is the rate equation. Okay? Now, if that was the rate equation and this is my mechanism, I should be able to pick which step is the rate determining step. Well, remember, if this was the slow step, then B has to be second order, which it isn't here. A would have to be first order, which it is. Okay? And C would have to be first order. But notice that C is not included in the rate equation. That must mean C is zero order. So C must be involved in collisions after the rate determining step. So if this was my reaction and this was the proposed mechanism, these are the collisions that have to occur, and this I knew was my rate equation, I know that my first step here would be the rate determining step because it shows A as first order and shows B as first order, 1A and 1B, and C is only involved in collisions below the rate determining step, so I don't have to worry about it. Okay, so the first step would be the RDS if that was the rate law. If the third step in that mechanism was the rate determining step, right? Let's say this step was the rate determining step, then A would be second order, B would be second order, and C would be first order. So if the third step of that mechanism was the rate determining step, then that would be my rate equation. Okay. Okay. All right, so what we want to take from this is, given the mechanism in the rate equation, we can determine the rate determining step, or given the mechanism and knowing what the rate determining step is, we should be able to figure out the rate equation, right? One or the other, okay? What if you're told a reaction happens in one step? Then that means the reaction itself is the mechanism, and that means the coefficients are the reactant orders. So if you were told this is a new reaction, let's say you have 2A and a B yields C. If you were told that happens in one step, then now you know that A is second order and B is first order because that is the mechanism. That is the only step, so it is the rate determining step. There's one B, so B is first order. There's two A's, so A is second order. Okay? All right. Another thing that a reaction mechanism will show us is a catalyst. Or what we should understand is if a reaction has a known catalyst, then there's two reaction mechanisms for the reaction. There's the uncatalyzed reaction mechanism, the normal reaction mechanism, and then there's the catalyzed one. So remember, what a catalyst does is it lowers the activation energy, but the way it does that is it provides a new pathway for the reaction to occur, and that means it provides a new mechanism. So reactions can have two different mechanisms. The one that doesn't include a catalyst, just the regular overall reaction mechanism, and then the one that does include a catalyst. All right, so let's look at the difference. All right, so let's say that this is my reaction. So we got two A's and a B yield C plus D. All right, and they say here is the mechanism one for the reaction. Here's a mechanism. It says A plus A yields C plus Z, and then Z plus B yields D. Okay? So Z is an intermediate, right? Because it gets produced and then consumed. All right? And there is no catalyst. All right? So this mechanism would be the uncatalyzed reaction mechanism. Why? How do I know that? Well, there is no catalyst, and we're going to show you what a catalyst is in a second. But there's no catalyst for this reaction. So based on this mechanism, a catalyst, if your reaction includes a catalyst, if it's the catalyzed reaction, the catalyst has to be a part of the mechanism, and we don't have a catalyst. All we have are reactants, products, and an intermediate. No catalyst. Okay. All right. So again, let's do some practice here. If this is my reaction mechanism, Z is an intermediate, and it would show A as second order because it shows up twice, and B would be zero order. So if this was my reaction, and this was the proper mechanism, this would be the rate equation for the reaction. A second order, B zero order. Okay. All right. And we know it's uncatalyzed because the mechanism doesn't show a catalyst. So let's show. Okay. If we add a catalyst, we get a new mechanism. Okay. A catalyst provides a new pathway for the reaction. Okay. It lowers the activation energy, so it speeds up the overall reaction, but the way it does it is provide a new pathway, a new mechanism. So let's say that this was our mechanism for this reaction. It says B plus W yields C plus Z. Z plus A yields D plus Y. And then Y plus A yields W. So we have two intermediates here. We have Z is an intermediate. We have Y is an intermediate. But we also have this new thing, W, that's in the mechanism, okay? But it cancels out. So if we add these three steps together, we end up with this reaction. We end up with 2A plus a B yields C plus a D. So we end up with that reaction, but we have this new thing, W, and it's not an intermediate. Remember, an intermediate has to be produced and then consumed, right? This is being consumed and then produced. That's a different thing, all right? And what we've just identified there, W, is a catalyst. So W is a catalyst. So remember, when I said intermediates cancel out this way, catalysts cancel out on this diagonal because they are consumed and then produced. So overall, they are not involved in the overall reaction, okay? They cancel out. Just like intermediates cancel out, but kind of a different way, right? Intermediates get produced then consumed, catalysts get consumed then produced, all right? So this would be the catalyzed reaction. How do I know it's the catalyzed reaction? Because the mechanism shows a catalyst, okay? So Z and Y are intermediates in this mechanism. W is a catalyst. And the rate equation would be B is first order, A is first order, and wait a minute, W is first order. So that's a new thing we have to understand. Notice W wasn't a part of the overall reaction, but it's included in the rate law. So not only does a catalyst provide a different mechanism for a reaction, so notice this is mechanism 2 for the reaction when it has a catalyst, and this is mechanism 1 for that same reaction when there is no catalyst, okay? So if you have a different mechanism, that means you have a different rate law, and we just figured out that if we do have a catalyst, it is included in the rate equation. So let's look at this mechanism. If we show if we use the slow step, the rate determining step, and anything above it, A shows up once, so A is first order. B shows up once, so B is first order. And W shows up once, so W is first order. And so we do include catalysts in a rate law for a catalyzed reaction. Okay, because a catalyst does affect the rate of a reaction, so it should be in the rate equation. Okay, so if a reaction is catalyzed, the catalyst does get included. Notice intermediates never are, and products are never included in the rate equation. But if you do have a catalyst, it is included in the rate equation. Okay, so here's our reaction, and it has two rate equations. It has the uncatalyzed rate equation, and we figured out based on the first mechanism, and it has a catalyzed rate equation, which is this one, and that was the second mechanism that created a catalyst. So what we want to understand after this lesson is we want to, if we're given a full mechanism, determine the rate equation. If you're given the rate law instead, and not the full mechanism, be able to determine the rate determining step. Identify intermediates, identify a catalyst if there is a catalyst in the reaction. Remember, if you have a multi-step mechanism, you're going to have intermediates, but you're not necessarily going to have a catalyst, right? If it's a catalyzed reaction, you'll have a catalyst, and the catalyst will show up in the mechanism. But if it's not a catalyzed reaction, it's just a normal reaction, then you won't have a catalyst. And if you have multiple steps, you'll have some intermediates maybe, but no catalyst, all right? And if you do have a catalyst, it is included in the rate equation, okay? All right, so that's where I wanted to go over today. Hopefully you find that helpful, and I'll be back later with kind of some practice problems, just to show you how 7-1 and 7-2 show up on the AP exam, all right? So have a good one.